Hello friends, class FYBSC, semester 2, subject electricity and magnetism, paper 2, chapter 5, magnetic properties of materials, lecture 2, second property, magnetic intensity, vector H. Whenever a magnetic field is applied across any material, it gets magnetized, as we know. The actual magnetic field inside it is sum of the magnetic field applied and the intensity due to the magnetization. We define a new vector field H such that vector H is equal to vector B divided by mu 0 minus vector M, where B is the resultant magnetic field and M is magnetization. The quantity H given by equation is called magnetic intensity or magnetic field intensity. The unit of H is the same as M, that is magnetization, that is ampere per meter. If no material is present, that is in vacuum, M is equal to 0. If we put M is equal to 0, then we get vector H is equal to vector B divided by mu 0. Whenever the end effects of a magnetized material are neglected, the magnetic field intensity due to the magnetization is 0. This may be the case with the ring shaped material. That means like this. Suppose this is ring shaped material. These possibilities are there. Or in the middle portion of a long rod like this. This may be in the case. Which one? See, whenever the end effects of a magnetized material are neglected, then magnetization is 0. With this ring shaped material or middle portion of the long rod, the magnetic intensity is then determined by external source only if the material is magnetized. For example, the magnetic field at the center of a long solenoid, N turns per unit length, N turns per unit length, carrying current I when no material is kept in it. The long solenoid is here like this. Take this example. For our convenience, this is simply what a solenoid. The coil is here actually. Okay. Now in this case, the magnetic field at the center of a long solenoid, N number of turns are there, suppose. Okay. These N number of turns are per unit length. N number of turns per unit length is there, and which carries the current I. When no material is there, that means simply we can say that only this solenoid is like no material is placed inside this particular space. No material is kept. Then this vector B is equal to mu 0 n into I. N is the number of turns per unit length and I is the current. That means whatever the current which is flowing through this. Hence, the magnetic intensity H is simply we can say that vector B divided by mu 0. Previously we see here. What is it? H is equal to vector B divided by mu 0. H is equal to what? Vector B divided by mu 0. Now put this mu 0 into Ni at this place. What we get? That value. That means the simple equation we get here. Vector B is equal to mu 0 Ni. We already have this thing. Then therefore vector H is equal to mu 0 into Ni divided by mu 0. Now this mu 0 get cancelled and the remaining thing is Ni. That means vector H is equal to Ni. When long copper rod is inserted in long solenoid, see here, this is the copper rod now, which is inserted in this solenoid. Solenoid is here, like okay, we already did this thing previously. Okay, in the long solenoid, the magnitude of magnetic intensity is same. That means H is equal to Ni. It turns out that for infinitely long solenoid with the same number of turns per unit length of solenoid, the magnetic field is constant in strength everywhere inside. That means long solenoid is there and same number of turns are there. Then this strength of magnetic field is simply we can say that constant. Therefore, we can say that the end effects are neglected. End effects are neglected. Then third, magnetic induction. Magnetic induction, that is a vector B again. Magnetic induction B is defined in terms of FB on the test particle with charge Q moving through the velocity vector V. Then using Lorentz equation, Lorentz force, vector FB is equal to Q into vector V into vector B. Unit of B is Tesla and denoted by capital T. 1 Tesla is equal to 1 Newton per ampere meter, and which is equal to 10 raised to 4 Gauss. Magnetic field can be created on the basis of 3 elementary ways. 1. Electrical currents, magnetic dipoles, changing electric field. These 3 elementary ways are there. All moving charges produce magnetic field. The magnetic field is generated by steady current, continuous flow of charge, steady current. For example, B through wire is described by Biot-Savart law and Ampere's law. We know it. We have discussed how to calculate the magnetic induction. How to calculate the magnetic induction. We already discussed it. There is a point due to the solenoid, toroid, long straight conductor, and current carrying circular loop in previous chapter. B and H are related in vacuum actually by the following equation. Vector B is equal to mu 0 vector H plus mu 0 vector M, which is equal to mu 0, which is common here, and bracket vector H plus vector M, bracket completed. In vacuum, we know that vector M is equal to 0, and vector B is therefore equal to mu 0 into vector H. The next, magnetic susceptibility, chi M. For most magnetic materials, that is para and dimagnetic materials, it is found that the magnetization M is always proportional to the magnetic field intensity H. That is, vector M is directly proportional to vector H, or vector M is equal to chi M into vector H, where chi M is simply the proportionality vector, where the constant chi M is called magnetic susceptibility. See here, magnetic susceptibility, chi M, which is a very important property of this magnetic materials. Magnetic susceptibility is defined as the ratio of magnetization M to the magnetic field intensity H. Magnetic susceptibility is defined as the ratio of magnetization M to the magnetic field intensity H, and mathematically it is given by chi M is equal to magnitude of vector M divided by the magnitude of vector